So suppose I have a group G, and then I have a surjective morphism from G to some other group G prime. And I'll give this map a name. Let's call it phi. So now let n is going to be the kernel of phi. So that means that n in particular is going to be a normal subgroup of G. So i.e. n is a normal subgroup of G. And because n is a normal subgroup, we can form the quotient group, G mod n. And so in this video, I'd like to prove the following theorem, which is known as the first isomorphism theorem. First isomorphism theorem of great importance. And it's a theorem about G mod n, and what it says is that G mod n is isomorphic to G prime. So G prime being the image slash the target of this morphism. Of course, the image being surjective, the image of the morphism phi will be G prime. And this is what the theorem says. And so in particular, we have more than just this isomorphism. We have the following, which is so G is going to map to G prime by phi, and then this is going to be let me call it P, the projection from G onto G mod n. And so the theorem says that we can fill in this diagram with another map. So let's call this map psi. Right, this Greek letter psi right here. So this map will be psi, and so the theorem is going to say that phi equals psi composed with p, or as I like to read this, psi after p. So not only are these things isomorphic, but they're isomorphic in a way that's compatible with this map from G to its quotient. Okay, so now how do we prove this? So to prove this, we need to, first we need to define phi. Okay, and then we need to show that phi is well defined. And the reason we'll have to show that it's well defined is because of our definition. So we'll see what this means in just a second. I'll put a little star right here. And then once we've gotten that phi is actually a function, we need to show that phi is injective. We need to show that phi is surjective. And we need to show that it is a morphism. Okay. So the definition of phi is going to be the following. So phi is a function, remember, phi is a function from G mod n to G prime. And so G mod n is a set of, say, left cosets. It'll be the set of left cosets of n. So an element in G mod n will look like an for some a in G. And, elements in G prime are just going to be, just elements of G prime. So the way we'll define the map is an is going to map to phi of a. So the idea is somehow this kernel, the idea of doing the quotient is the elements that we're quotienting by become trivial somehow. So the idea is that these guys that are in n, multiplying by anything in n, doesn't matter. And because the kernel is going to be things that map to the identity, right? The idea is that we only need to care about the part of this coset that has nothing to do with n, that's outside of n, say. So that's sort of a high level sort of philosophy statement, but enough philosophy. Let's prove something. So the problem with making a definition like this is that we don't know that this definition is well defined. Which is to say, like, if we take two different cosets, will they map to the same element in G prime? And so that's why we need to show that phi is well defined. It actually has to do with, the definition that we chose is not obviously well defined. And so that is to say, we need to show that if an equals bn, i.e. a and b are in the same coset, that is going to imply that phi of a equals phi of b. So what we need to show here is we need to show that there's a relationship between cosets of n and applying the map phi. And so in order to show this, what we can do is, okay. So what I'm going to do to prove this is I'm going to use an intermediary condition, right? Intermediate step. But before we do that intermediate step, I want to make a comment on, so like this step might seem a little bit like it's coming out of nowhere. And so I want to illustrate why we would take this intermediate step before we actually take it. So let's consider maybe over here phi of a equals phi of b. So rather than starting from the thing that we know, let's start from the thing that we're trying to prove and work backwards. And so we know, so if phi of a equals phi of b, we're trying to think about the kernel. We're trying to think about n. And the thing we know about n is, well, it's a normal subgroup, but it's also a particular normal subgroup. In particular, it's the kernel of phi. So in particular, we want to take this equation and see if we can, find something that's in the kernel. And we can if we multiply on both sides by 5b inverse. A 5b inverse equals 1. And then we can pull the inverse inside. So this will be equal to 5a 5b inverse, because it's a homomorphism, which will be equal to 5ab inverse. Right? So what we've shown is that 5ab inverse equals 1. And we draw a little box around this, because that's kind of important. And the reason it's important is because now we've found something that's in the kernel, particular AB inverse. So this is something that, so this is, right, this is the same thing. 5a equals 5b is the same thing as saying that 5ab inverse equals 1, i.e. I guess we should say AB inverse is in the kernel of phi, which is n. Okay, so with that idea out of the way, let me tell you what the intermediate step is. So the intermediate step is we're going to show that an equals bn if and only if, or just if, A inverse B is in n. And then, by what we've shown here, right, we can go both ways with this. If A inverse B is in n, this is the same thing as saying that phi of A equals phi of B. I guess I have A and B switched here, but this equation is symmetric, so it won't matter. So the first step in the proof, and so this, okay, and so, but this step isn't as hard because we can say an equals bn. Well, we multiply on the left by a using this sort of product of sets notation, so that we have a inverse an equals a inverse bn, but this is just going to be n. So n will equal a inverse bn, which is the same thing as, so now because these two cosets are the same, everything in this coset is in this coset, and in particular a inverse b is in this coset. So that shows that a inverse b is in n. And so now, to finish the proof, we just do this backwards. A inverse b, not a b inverse, but a inverse b, although it doesn't matter. This is in the kernel, therefore this is equal to 1, and then do this multiplication in the opposite direction. Okay, so that shows that phi is well defined. And what the interesting part is that turns out to be the hardest part of the proof. Because showing that phi is injective, well, any element of, so the cosets of n, or in G, which are the elements of G mod n, are going to be the same as the fibers of the map phi. That's exactly what we've we've shown here, right? We can just as easily make this be if and only if, again, just by doing the proof backwards. It's sort of every step is an if and only if. So what that means is that anytime two cosets are the same coset, 5a is going to be equal to 5b, but but the thing is that if we have two different cosets, then that means that we're going to get two different things in G prime. So that will show that phi is injective. So we just need to do the same proof backwards. And if you're not okay with this, if this doesn't make as much sense, I encourage you try to do this out on your own. To show that phi is surjective, well, that just follows from the fact that I guess I should say psi. Really, I meant psi everywhere I was writing here. Phi and psi are so related because they're we can kind of maybe not worry too much about the fact that I wrote phi instead of psi, but the point is that the map we're really talking about, that we're defining, is, this map right here. And the reason it's surjective is because phi is surjective. It's very easy to check that this map is just first we apply, if we first apply the projection map, then we apply psi, we get exactly the map. We get exactly the map phi. And then the fact that this is a morphism will be, again, because phi is a morphism. And so I would encourage you to write this out if it's not immediately obvious, but and that's totally okay. But really, the way you're going to prove this is you're going to start from the fact that phi is surjective. Look at the definition of psi. Phi is in the definition of psi, and because of that, this will tell you that psi is actually surjective. And same with the morphism property. The proof will be extremely similar.